Tell us a little bit about your institution.
Sure. So, yeah, I'm at University College London. In my PhD, and I guess we're a fairly significant group of people working on this experiment. So we're like a plurality, but not a majority of people in collaboration, I think. So we've got quite a few of us, specifically myself doing simulation and analysis, more people doing different atomic and molecular group doing magnetometry and atomic source production. Yeah, so there's a good number of people at UCL working on this.
How big is your department? And
how big is UCL? Well, so the high energy physics group total is, I think we're close to 80 or 90, including with faculty, postdocs, and grad students. That's spread across a lot of experiments. The university itself. So yeah, good question. Anyone to guess? I think it's, we're talking tens of thousands, but it's one of the biggest institutions in the UK now, I think.
Maybe get started. Okay, great. So thanks everyone for coming. So today we have the pleasure of hearing from Dr. Seb Jones. Seb received his PhD from University College London in early 2022, and having worked on Dune and an associated test beam experiment there. And for the last 2.5 years, Seb has been a postdoc at UCL, working as part of the Quantum Technologies for Neutrino Mass collaboration. Within the collaboration, Seb's work primarily focuses on experimental simulations and the analysis of those simulations, with the aim of optimizing both an upcoming demonstrator experiment and any future neutrino mass experiments. Take it away, Seb.
Okay. Thank you very much. Yes, thank you for coming here today to give this seminar. As mentioned, I'm from the Quantum Technologies Neutrino Mass collaboration, and I'm going to be talking about collaboration and the demonstrator apparatus we hope to build and the work that's been going towards that. So just as an outline of the talk, I'll talk about neutrinos and neutrino mass measurements to give some background and talk about why this is an interesting measurement to make. Then I'll talk about cyclotron radiation emission spectroscopy, or CRES, why that's a good technique for trying to measure the mass of the neutrino. And then I'll go into more depth about our collaboration and the work we're doing, and how we go about using this technique. Okay, so some very quick background on the neutrino. It was first postulated by Pauli in 1930 to explain the non-anomalous shape of the beta-decay spectrum. So initially, when beta-decay was observed, we just saw the outgoing beta particle and the leftover nucleus. So it looked like a two-body decay, in which case when you look at the energy spectrum of this decay, you just expect to see like a delta function. However, what was observed is this continuous spectrum, which implied that there was in fact a third body, the then as yet unobserved neutrino. So this was directly detected by Cowan and Rains in 1956, and throughout the 20th century, 3 flavors were discovered, which correspond to the 3 charged leptons that we observed: the electron, the mu, and the tau. And so far, all of these neutrinos appear to be massless. So, moving from the end of the 20th century into the 21st century, we have a lot of we have overwhelming evidence from atmospheric, solar, reactor, and accelerated neutrino experiments that all confirm the existence of the phenomena that we call neutrino oscillations. And indeed, in the 2015 Nobel Prize was awarded for the discovery of this phenomenon. Now, crucially, the observation of neutrino oscillations shows that neutrinos have mass. This is something that can't happen if neutrinos are massless, as was originally theorized. Now, these oscillations arise from mixing between the flavor and mass eigenstates of the neutrinos. And one thing that is interesting from our current observations and current best limits on neutrino masses is that the mass scale, the neutrino mass scale, appears to be extremely different from that of the other fermions. That's just illustrated on the right here. So you can see that several orders of magnitude exist between the masses of the neutrinos and the masses of the next lightest fermions. So we've got the electron here separated by five or six orders of magnitude. So neutrino oscillations, as I mentioned, occur because there's this mixing between the flavor and the mass eigenstates. And this mixing is just controlled by the PM and S matrix, which is matrix U here. So the oscillations are controlled by this matrix and the squared differences between the mass eigenstates. So what I've called here, what was commonly called delta M squared, and then I and J are just your mass eigenstates, which are referred to as M1, M2, and M3 commonly. And these delta M squared control the length and energy scale at which oscillations occur. We do actually have some information on these delta M squared. So oscillation experiments have led us to be able to measure these all to a reasonably good precision. They're known to within better than a few percent. However, the ordering of these mass eigenstates is currently unknown. So this is what we talk about with resolving the neutrino mass hierarchy. We currently aren't able to distinguish between the two scenarios displayed over on the left here. So we don't know whether the lightest mass eigenstate is M1, which is what we call the normal hierarchy or the normal mass ordering, or if M3 is the lightest mass eigenstate, which is what we call the inverted hierarchy or ordering.
Quick question. There's an easy way to explain why there's that ambiguity or where it comes from?
So the oscillation probabilities don't depend on the absolute values of they depend on the squared differences. They don't depend so that doesn't give you any information about the sign of what M3 minus M1 is. So if you go through and calculate the oscillation probabilities, you find that we don't have information in a vacuum, I should say, from about this, about if M1 or M3 is heavier. The only way you can get that information is through matter effects. So that's what the next generation of oscillation experiments hope to be able to determine by passing the beam through long matter, high matter densities, or through large amounts of matter. You can see maybe determine this hierarchy. So it's possible that the lightest mass eigenstate, so either M1 or M3, may in fact be massless. So one can then constrain the masses of the other eigenstates from these measured mass splittings. So that's just what's displayed here. You can see on the x-axis of each of these plots is the mass of the lightest mass eigenstate, and you can then see that the other two eigenstates are then constrained as that the mass of that lightest eigenstate falls to 0. So why is it interesting to measure the absolute scale of these neutrino masses? So it's one of the most abundant particles in the universe. So I think potentially the most abundant fermion. And we don't know its mass. So purely from an understanding of our universe, I think this is an extremely interesting question to answer. The extremely different mass scale of neutrinos suggests they have a different mass generation mechanism compared to just the Higgs mechanism for the other fermions. And knowing the mass would be an important input for this. And it's connected to various other areas of physics. So electron number violation, cosmology, sterile neutrinos. These are all areas that are related to this. So how do we go about doing this? So there are kind of three ways that we can access information about these neutrino masses: cosmology, neutrino mass double beta decay, and direct measurement of beta decay. And this direct measurement is what I'll mainly be talking about today, but I'll give an overview of the limits from the other two. We actually measure slightly different parameters with each of these. So for cosmology, we measure the sum of the neutrino masses. For neutrino double beta decay, we measure this n beta beta parameter. And then finally, when we measure beta decay directly, what we actually measure is this weighted sum of the neutrino mass eigenstates, which I called here n beta. This n beta parameter is going to get mentioned a lot, so worth remembering that when people talk about the neutrino mass that you measure in direct measurement of beta decay, this is what you're talking about. So these are all interesting methods, and they all provide the useful information, but they do have their issues. Cosmology relies on your understanding and of the current cosmological models that we have, and so your confidence in the limits that gives you is obviously related to your confidence in those models. And neutrino double beta decay, this is a process that only occurs if neutrinos are Majorana particles. In the case that neutrinos are Dirac particles, this process doesn't occur, and so we can't obtain any useful information from either observing it or not observing it. So in short, neither of these are model-independent measurements in the same way that direct measurement of beta decay is. So to illustrate this, the total energy of the initial state is well known. You can measure the mass very precisely of a given atom. And the kinematics of your final state can be precisely measured. So you can measure very well the energy and of your outgoing electron. Then all you really have to assume in order to extract some neutrino mass is that energy and momentum are conserved. So this is what we call direct measurement. And the isotope that is commonly used for this, and that I'll be discussing in reference to our experiment today, is tritium, which decays producing electron antineutrino, and a helium-3 nucleus. So this is actually quite an old idea. So this is from 1934. Fermi suggested that you could use the shape of the beta decay spectrum to determine the neutrino mass. So that's what you're seeing here. You're seeing this mu equals 0 curve for a massless neutrino, for a small mass, and for a large mass. And it's basically the similar idea is still used today. The idea is that the presence of a non-zero neutrino mass or masses leads to a distortion in the end of this beta decay spectrum. And this is just an approximation for what the end of this spectrum currently looks like. So I plotted several curves here, the black dashed line for a massless neutrino, and then stepping up through several different values of n beta. And what you can see is that when we're talking about these n betas of 1 eV or less, the information about this is all encoded right at the end of the beta decay spectrum. So to give you an idea of the kind of differences you're looking at, you can see that these are all happening at the 1 eV level towards right at the endpoint of the beta decay spectrum. For comparison, the endpoint energy for tritium is 18.6 keV roughly. So you're looking at only a very, very small fraction of the decay spectrum. So current limits, it sounds like this is extremely challenging, but there is a kind of lower limit on what we can measure. So we know that neutrinos have mass, and we've been able to measure the delta M squared, the mass splittings pretty well, and we've been able to measure the elements of the PM&S matrix pretty well from oscillation experiments over the years. So one can actually calculate a lower limit on this M beta parameter, depending on if we live in a world where we have a normal or inverted neutrino mass hierarchy. So you get this just by assuming that your lightest neutrino mass eigenstate is massless. And what you find is that if we live in a world where we have this normal neutrino mass hierarchy, your M beta has to be greater than 9 millielectron volts. And for an inverted hierarchy, it has to be greater than 50 millielectron volts. So this is, quite exciting. So if you are able to build an experiment with a sensitivity below 50 millielectron volts, and for example, you don't measure a neutrino mass, you've determined the mass hierarchy, and if you can, get to these tiny sensitivities of 9 millielectron volts, there's this kind of tantalizing possibility of getting a guaranteed discovery. You either measure a neutrino mass, or if you don't measure a neutrino mass, there is something completely unexpected going on. So this is, very exciting prospect in terms of constructing an experiment to have this guaranteed discovery. I mentioned that this parameter, can be used to inform other areas of physics. So you can plot this M beta parameter on the x-axis here for both of these plots against the parameters that you would extract from, on the left, neutrinoless double beta decay experiments, and on the right, cosmological measurements. So you can see that positive measurement of the neutrino mass from direct measurement experiment has the potential to confirm or deny some of these either cosmological models or neutrinoless double beta decay models. So over on the left, this grey band is the current upper limit on double beta decay from Canada Zen. And over on the right, this magenta dotted line is from recent cosmological measurements. So the neutrino mass, according to these measurements, lies below this magenta line. So what we can see is that if you were, for example, to make a measurement of M beta at, say, 0.2 or 0.3 eV, you would also have some understanding that your cosmological measurements were not correct, and you were, maybe there was some lack of knowledge about our current models of the evolution of the universe. So how do we go about doing this in a current state-of-the-art experiment? So the best measurements come from the KATRIN experiment, which uses what's called a Mackey filter, magnetic adiabatic collimation with an electrostatic filter. So the idea is this: you have your electrons from your tritium, and they're emitted in some source region over on the left here with a high magnetic field, and they then travel adiabatically along the field lines to an analyzing region with a much lower field. At the center of this spectrometer, there's a retarding potential which prevents electrons without sufficient energy from passing through. Those electrons with sufficient energy to pass this potential barrier are then re-accelerated and detected. So the idea is you repeat this for multiple different retarding potentials, and then you generate the spectrum by repeating this process, changing your retarding potential. You can build up a picture of the end of the beta decay spectrum. So this has been a pretty successful technique thus far. So over on the right, here's limits from current and past Mackey experiments. So the upper two lines from the final results from two experiments, the Mites and Troits experiment. This orange dotted line is the most recent result from the KATRIN experiment, currently the world's leading constraint on this M beta parameter. And the expected final sensitivity of KATRIN is plotted as this orange dot dash line. So this is going to take us to this region here. So we're still somewhat below this region where we determine the mass hierarchy. And we're still a couple of orders of magnitude away from or an order of magnitude roughly away from determining, getting to this point where we have a guaranteed discovery. So why not just continue with this current MAC-E technique? So at the moment we have this KATRIN experiment on the left. The beam line here is about 70 meters long. The spectrometer is about 10 meters in diameter and 23 meters in length. And it's all held at a pressure of 10 to the minus 11 millibar. So it's pretty large, and it's no mean feat to build something like this where you have precise control over the magnetic fields in such a large volume, and you're keeping things at such a high vacuum. So to increase your statistical power, you can increase your source size. However, your source thickness is limited by your scattering cross-section multiplied by your source number density to avoid collisional losses. Once your decay electrons scatter off residual gas, and if you haven't measured their energy, you don't have any useful information about the tritium beta decay spectrum. So you want to measure them before they scatter. For a MAC-E filter, you can your filter width, say delta E over E, is just given by this relation here. And for KATRIN, this delta E value is 2.8 eV. So if you want to increase your source size, you can increase your source radius rather than increasing the thickness. However, if you don't want to degrade your filter width, there has to be a corresponding increase in the spectrometer size. You have to increase the size of your analyzing plane also. Then if I just show you an image of the current KATRIN spectrometer being moved into place, it perhaps gives an idea of why this is not feasible to do. This is already a huge experiment. As I mentioned, you've got to have this very precise control of the magnetic fields within there. It's already held in a vacuum. So to go to this 0.2 EV, we require a different technique.
Is that a real picture?
That's a real picture, yeah.
Where's it going?
It's going to the lab in Karlsruhe.
But where is it moving? How's it being moved to?
I think it's on a trailer. So I think this is pulling it or something behind it. Okay. So the technique that we believe has the potential to kind of break through this 0.2 EV is CRES, Cyclotron radiation emission spectroscopy. It's a concept pioneered by the Project 8 collaboration. And the idea is this: beta decay electrons can be immersed in a magnetic field. They emit electromagnetic radiation, and the frequency of this radiation depends only on the electron energy and the magnetic field strength. So it's just given by this simple formula up here in the upper right. What kind of radiation are we talking about? Well, if you plug in the values for the endpoint of the tritium beta decay spectrum in a 1 Tesla magnetic field, you find that you get a frequency of about 27 gigahertz, wavelength per centimeter, so microwave radiation. And the idea is that you're then able to collect this radiation with antennas, a waveguide, or a resonant cavity. So why is this such a good measurement? So frequency measurements are measuring the number of cycles over a period of time is a technique that is resistant to a lot of sources of noise. So you can reach a precision of like parts per million with frequency techniques, which is useful because we're trying to measure energies down at the kind of ppm level when we're measuring 1 EV in a 18 or 19 keV spectrum. You don't have any losses, so unlike a MAC-E filter, you don't have to transport your electrons from your source to your detector. You can actually have your RF collection directly observing your tritium atoms. So that means that you don't have to transport these electrons, which means fewer losses to scattering. It all helps increase your statistical power. You get to measure as many more events for a given exposure of tritium. And you can do this because the source, so tritium gas, is transparent to microwave radiation. And finally, a CRES spectrometer is what we would term a differential spectrometer. So a Mackey filter is an integral filter. As I mentioned, you set your filter to by setting the retarding potential to a given level, and then you measure the intensity above some point. And that means that electrons that are going into your spectrometer that don't have enough energy to pass your filter, you don't gain any information from them. And so you lose those statistics, even though they potentially contain information that could be useful. So this means that you require extra time for measuring your background, your spectral intensity, and your endpoint energy. Differential spectrometers, like those using CRES, don't have this issue. You can measure the whole spectrum at once, or as much of the spectrum as the bandwidth of your instrument allows. And you can measure these events, you can measure these on an event-by-event, energies on an event-by-event basis. There are challenges. So the radiated powers that you get are very small. So this is your formula for the Larmor power in free space. So if you plug the the relevant order of magnitude numbers in for a 1 Tesla magnetic field and an endpoint electron, what you find is that your radiated power is only about 1.2 femtowatts. So you're trying to measure some very, very tiny powers relative to potential, thermal noise and things like that. Atomic tritium source is required. Now, strictly speaking, you would need this to make a more sensitive, Mackey filter as well. But it's also worth mentioning that this is something that has to be overcome to get to any kind of sensitivities below 0.1 or 0.2 EU. So the problem is molecular tritium has these rotational and vibrational excitations that broaden the endpoint peak. So that's just what's illustrated over on this plot on the right. Whereas atomic tritium doesn't have these issues. So in order to build this kind of the most sensitive experiment, you have to have an atomic tritium source. And the production and preservation of atomic tritium is therefore a key challenge for any future experiment. KATRIN, as the experiment I was talking about before, uses a molecular tritium source. So this is one of the big research areas or big challenges that has to be overcome to make this most sensitive experiment. You have to try and observe a lot of tritium atoms. So if you do some back of the envelope sensitivity calculations, you find that you need to track and observe roughly 10 to the 20 tritium atoms for around about a year, which is quite a high exposure. And the reason for this is that the last electron volt spectrum, where all the interesting information about your neutrino masses contains a very tiny fraction of the events. So the last electron volt I've got here contains about 2 or 3 times 10 to the minus 13. That's a fraction of the total events.
You need to observe the same 10 to the 2 for a year.
Or you need to have more tritium atoms than 10 to the 20, and you certainly cycle them through. I mean, in practice, it's the latter. You're not going to be observing the same 10 to the 20 yet. You have some kind of recycling of the atoms. You have a larger total mass than 10 to the 20 would imply, but you
don't observe them all
don't observe them all at once.
They have decay. They don't stand around, right?
It's true. Well, how many of them decay? What's the half-life?
12 years.
Okay, well, then you use quite a bit.
but for comparison, I think that the KATRIN inventory is order 10 grams, maybe. And so finally, your magnetic and electric fields need to be extremely well constrained. So this formula is kind of deceptively simple. The understanding the magnetic field experienced by an electron is absolutely key to extracting this kinetic energy from a frequency measurement. You might be able to measure the frequency very precisely, but if you don't know your magnetic field equally well, you're not going to be able to extract your kinetic energy. And you also have to be able to minimize and or constrain any electric fields in your detector. So any unintended electric fields from adsorbates or imperfections on cold surfaces are going to change your electron's energy. They're going to lead to stray fields that over time will wash out your electrons' starting energy. So it's absolutely key that you minimize those. Just got a few Project 8 collaborators in here, so I'll just flash up one slide. This is the current leading CRES experiment. So these are some recent results. So over on the left, this is what we call a spectrogram. So time on the x-axis, frequency on the y-axis. So this is typically what an electron event looks like. You can see this characteristic chirp as the this upward slope as your electron's radiation increases in frequency, and that's just from your electron losing energy. You have these discrete scatters which come from your electron scattering off gas, and these are just from a krypton source which was in their phase 1 experiment. And then over on the right, you can see the results from the phase 2 experiment with molecular tritium in a roughly 1 Tesla field. So about 3,000 or 4,000 events detected over 82 days, and they were actually able to make a measurement of the tritium spectrum. And this is all with a relatively small volume, measurement volume. So I think the actual volume that they used to get these results was order centimeters cubed. So, and within that, they were able to set a limit on the on this M beta parameter. So even with that relatively small volume and small exposure. So this brings me on to QTNM. So we are quantum technologies for neutrino mass. So it's a collaboration between these institutions that's all UK based at the moment. And the idea is the original proposal was to build a demonstrator apparatus for determining the neutrino mass by CRES from tritium beta-decay. And we call this proposed demonstrator apparatus imaginatively CRES. So what does this entail? Well, for these large exposures, you want high densities of tritium atoms. So demonstration of confinement of atoms with densities of order 10 to the 12 per cubic centimeter, with the idea that the methods demonstrated would be scalable to these exposures of 10 to the 20. Extremely precise electric and magnetic field mapping. So want to demonstrate magnetic field mapping with sub-microtesla absolute precision and millimeter scale spatial resolution, and observation of CRES from electrons, initially from a non-tritium source, potentially with these quantum noise limited microwave detection systems. This is what the pathway looks like. So we're currently in this upper stage of basic technology demonstration. The idea being, as I mentioned, this would all be done with a non-tritium electron source. But beyond 2025, this experiment would be built such that it could be moved to the Culham Centre for Fusion Energy, which is located where this pin is in the UK. So this is the current location of the Joint European Torus. So they have the capacity to deal with the large amounts of tritium required for an experiment like this. And then looking ahead, the idea would be that in the 2030s and 40s, there's potentially some consolidation with other tritium-based neutrino mass experiments. And you go towards a final neutrino mass experiment with 10 milli-electron volts or 50 milli-electron volt sensitivity, either at Cullen or a similar facility where the capability to handle the correct amounts of tritium exist.
So what is the relation to Project Blue?
So we have a consortium agreement with Project A, but we're two different collaborations, and the idea is that we're pursuing some different but maybe like complementary avenues. So they're both CRES-based, but with two separate collaborations. Okay, so this is an outline of this CRES apparatus. The idea is we have a source where we start with tritium molecules that are then disassociated into tritium atoms, and they form a beam that is then passed around a storage ring, passing through what we term like a CRES region. And in the CRES region, that's where some of our tritium atoms decay, producing the decay electrons, which emit cyclotron radiation. This cyclotron radiation is then amplified in the quantum limited amplifiers, and then finally our frequency metrology is performed, and we perform an energy measurement on each electron. And this is a kind of basic schematic of how we envisage this CRES system looking. You have your atomic source, which is this supersonic beam. So hopefully at this point you just have atoms that have been produced. These atoms then state selected into so that only these low field seeking states pass through, and these neutral atoms in these low field seeking states are then trapped within this magnetic storage ring. And the idea is that they circulate in this storage ring multiple times and pass through this CRES region multiple times. And in this CRES region is where this cyclotron radiation is measured.
So can you talk about the storage ring a little bit?
I'll come on to that, so I've got some slides. So I'll just flash these up again and say these are some of the track challenges from Neutrino Mass with CRES, just as a reminder, because I'll kind of talk about how the work we're doing relates to these challenges. So we have our atomic source. So as I mentioned, we need, for the most precise measurements of beta decay, you have to have atomic tritium rather than molecular tritium. So fortunately, the endpoint atomic tritium of molecular tritium is higher than that of atomic tritium. So if you have molecular contamination, it will act as a background. So to that end, at UCL, this atomic source has been constructed, and it consists of this. Well, at the moment, it's being demonstrated with hydrogen rather than tritium, but the idea is that this hydrogen is dissociated using this DC discharge, which is seeded with electrons from a tungsten filament, and that's what you can see here. So I think this glow is actually from filament. These atoms then pass through a skimmer, and hopefully you end up with a relatively pure beam of atoms. At UCL at the moment, we're characterizing this source. So our atoms are having been produced. We try and characterize this source by using this REMP technique, where multiple photons are used to ionize the atoms before they're collected on an MCP. So what are the current results we have? So at the moment, I think the technique with an unoptimized system produces atom number densities of about 10 to the 10 per cubic centimeter. But crucially, this beam has a very low velocity spread. So although the hydrogen, our beam has a longitudinal speed along the storage ring of, I think it's between, it's around 1,000 meters per second. The spread in the velocities of these atoms is quite small. So it's about 20 meters per second for hydrogen. And this is also a really nice feature to have because if you have very hot atoms, you will get some Doppler broadening of your cyclotron radiation. So that can also wash out your or help contribute to the resolution of any energy measurement you make of your electrons. So, having produced these atoms, they pass into this storage ring. So this storage ring confines the atoms using these hexapole magnets. It keeps them away, prevents them forming molecules on cold surfaces. So there are some advantages of this storage ring, particularly compared to, or we believe there are some advantages compared to using a trap. So with the storage ring, you don't have to load a trap, and in doing so, decelerate and cool your atoms. So the thinking is that that not having to load this trap leads you to having lower atomic losses and allows you to maintain that intense tritium source. It also separates your magnetic field requirements for CRES and atomic trapping. So the magnetic field that you want to do your electron spectroscopy is not necessarily the same as the field that you want to do to trap your atoms and keep them away from the cold surfaces. The advantage of this is by making your atoms into a beam, you can separate out those two magnetic fields. There's also a case that this could provide a scalable solution for a future neutrino mass experiment. So one can imagine a situation where you have multiple CRES modules connected by a single storage ring. And in this case, you could progressively upgrade the exposure of your experiment by adding more modules without the need to completely reconfigure and construct a new experiment each time.
I'm just a little confused. So the atoms, they're not continuously running around the storage ring, or
No, they're going continuously.
right, so they just pass through the CRES region.
Yeah.
Incidentally.
Yes, exactly. Yeah. Yeah, and then the idea is that you have enough in there that there is always, for some future experiment, that you would always have this 10 to the 20 in your field of view at a given time. Okay. So we also, turns out, need to trap our electrons. If you work out the change in frequency as a function of electron energy at 1 Tesla, you find that you get about 51 kilohertz per EB. Therefore, if we want to measure a width in energy of 1 electron volt at 1 Tesla, that's equivalent to a width in frequency of about 50 kilohertz. So for an FFT, for example, this would lead you down to saying, okay, we need to observe our electrons for more than 20 microseconds in order to obtain this frequency precision. If you didn't trap your electrons, an electron that was traveling very, very close to perpendicular to your magnetic field, 89 degrees, is going to travel 275 meters parallel to your magnetic field at this time. So you have to do some sort of magnetic trapping, or you have to do some sort of trapping to contain your electrons and keep them in the field of view long enough to make precise enough frequency measurement, and also to collect enough power that you can actually see, detect your electrons against your noise background. So the solution to this is to trap them in like a no-work magnetic trap, where they can be continuously observed for tens or hundreds of microseconds, undergoing periodic motion, which is illustrated in this plot on the upper left. And this magnetic trap is just a magnetic bubble. It's a local minimum in the magnitude of a background B field. And so the trapping field is of order millitesla for a 1 Tesla background field, but you can calculate the exact choices you would need to trap specific angles using this formula here. The trap design has a large effect on the range of observed frequencies. So understanding this trap design is absolutely key. So this is just illustrated here. So electrons with pitch angles of less than 90 degrees, so not exactly perpendicular to your magnetic field, undergo some kind of periodic motion in the trap. And as a result, they experience different average magnetic fields. A deeper magnetic trap will trap a higher fraction of your electrons, but they'll radiate at different frequencies. So this is showing that for sets of monoenergetic electrons or different pitch angles, what you can see is that they will actually radiate by tens of megahertz difference to those to other electrons of the same energy at different pitch angles. So you have to correct for this in order to make a correct measurement of your electron's energy. You have to use other features of your signal to get the best energy resolution, because you'll never be able to get the required resolution if you don't correct for its experienced magnetic field. So, I mentioned that this microwave radiation is suitable for collection with a lot of different technologies. So antennas, waveguides, cavities, multiple options are currently being developed. There's kind of a trade-off between some of these methods. So, for example, antenna arrays, you can use a beamforming technique to localize your electron, and this is useful because you can precisely determine where in your magnetic field your electron is. With the result that if you have some spatial variation of your magnetic field, you can then hopefully correct for this. However, the flip side is that many channels can be required to collect your sufficient power. Quickly becomes expensive in terms of equipment and computation required. Currently, on this side of things, we have some people fabricating arrays of patch antennas. Over on what we call circular antennas, so waveguides or resonant cavities, you can collect a large fraction of radiated power with one or a few ferrite probes. And if you build a cavity, your effects will actually result in an increase in the power emitted by your electron if your electron isn't close to the resonant frequency of your cavity. It's at the antinode of your cavity mode. However, you have your disadvantages. So your size of your cavity is coupled to the wavelength of your radiation. Your cavity is really constrained to be roughly order of size, lambda cubed. If you want a bigger volume, you have to go to a lower magnetic field, and then your radiated power scales with your magnetic field squared. So there are trade-offs involved. And so some of our collaboration members actually published a detailed analysis of some of the trade-offs involved in this paper here. So simulation and analysis, we've done quite a lot of work on this. So we're working to optimize our trap and RF collection design to make the most sensitive experiment we can. To this end, we've kind of written of software packages, both Germ4 based and standalone, that allow us to simulate decay electrons in a variety of traps, which, as you can see, output from this signal like into a spectrogram without noise, just over on the right here. And this simulation stack includes electron propagation in magnetic fields and electric fields, microwave collection, and a model of signal processing. And as I mentioned, you can use a lot of the information from these events to constrain your electron energies. The chirp rate, so the rate at which frequency increases, tells you about the rate of energy loss of your electron. This is related to the angle at which your electrons are traveling relative to magnetic fields. So that there's information there. As your electron moves in the track, depending on the exact readout system you're using, or the exact microwave collection system you're using, this varies, but you can get sidebands which are caused by amplitude and frequency modulation of your signal. And these also tell you something else about the axial motion of your electron. Often the spacing of these sidebands is related to the frequency of this axial motion. So you can also use this to try and pick apart the dynamics of your electromagnetic track. And then finally, you have these discrete jumps in frequency that are caused by scattering from your residual gas. You need to understand how often you observe these, how often they happen, and how often you observe them, in order to understand how often you're reconstructing your original frequency correctly. So this is kind of a schematic outline of what the spectrometer itself looked like. I've talked a little bit about the microwave collection devices over on the left. The idea is that we will be detecting CRES at cryogenic temperatures. So currently these electrons, we hope in a 4 Kelvin stage. The signals from the microwave collection devices then go through these quantum limited amplifiers in two-stage amplification systems. So they go to quantum amplifiers and then to conventional cryogenic pentamplifiers, with the hope being that this can overcome the small signal power. And we'd also have an electron source to calibrate the energy of this cryogenic vacuum stage. The amplified signal would then pass into the warm electronics, where it's downmixed to a frequency that would be efficiently sampled by like an analog to digital converter. So I'll talk a bit about the microwave amplifiers. Our CRES signal is very weak, and our state-of-the-art amplifiers have noise temperatures of around 7 Kelvin. And the overall added noise of your readout chain is dominated by the first stage of amplification. So to that end, we want these quantum limited amplifiers. So where the added noise is as close as possible to the standard quantum limit of half quantum. So within our collaboration, people are pursuing two different designs: these slugs and superconducting parametric amplifiers. So these slugs are these non-parametric, low-noise cryogenic amplifiers, which are currently under development at the National Physical Laboratory in the UK. And these are based upon these niobium nanobridge junctions that are fabricated, with the idea that these should allow for operation at high frequencies. So some numerical simulation has happened with these, has been done with these slugs, which is what is being shown in these two plots here. The upper one is the gain as a function of frequency, and on the lower one is the noise. And what you can see is that from these simulations, these slugs have the potential to provide high gain over a bandwidth of several gigahertz, which would be ideal for a system where you wanted to measure a large part of the beta-decay spectrum. So kind of work is ongoing to characterize and tune these designs. And kind of one maybe interesting feature of these devices is that these different color lines show the potential for tuning the amplifiers. So by changing the DC flux bias, I think it is, you can actually move where this gain peaks. So gives the potential for looking at different bits of the spectrum. At Oxford and Cambridge, meanwhile, there are these superconducting power amps being fabricated. So these are based on superconducting niobium nitride resonators. we have these, you can see that these have a slightly smaller bandwidth. So more like megahertz kind of scale for these amplifiers, but you get these high gains of 20 to 30 dB across these bandwidths. And these can, I think these can be produced in large quantities relatively easily. So that's currently being investigated. And finally, I think I mentioned that we want to measure our magnetic fields extremely precisely in order to achieve our electron. So at UCL, we have this work going on this Rydberg atom magnetometry and electrometry. So the idea is that you can prepare these circular Rydberg states using the atoms, potentially using the atoms that you are trying to measure, and this allows you add them into these circular Rydberg states and pass them through the volume where you want to measure your electromagnetic fields. You can then use pulses of microwave radiation to drive these Rydberg transitions, which are extremely sensitive to magnetic and electric fields, before imaging the electrons. And the idea is that you should be able to measure 3D maps in situ of your magnetic and electric fields, hopefully with a spatial resolution of better than 1 nanometer.
Using the detector itself, measure.
Exactly. You can do this either with helium atoms or with hydrogen or tritium atoms. Yeah. So current results, this is all done at low fields of about 1.3 millitesla. We've actually managed to achieve these field precisions of 2 microtesla and a relative precision of even below microtesla, down at the hundreds of nanotesla level. This is combined with a spatial resolution in 1 dimension of sub-millimeter. And also some extremely impressive electrometry measurements as well. These are just a selection of plots from the paper that details this method and results. The next step is to prove the viability of this method at higher fields, so more like 0.1 Tesla, and move towards this 3D method rather than just doing things in 1D. Okay, so to summarize, the neutrino mass scale remains unknown, but the answer is has the potential to provide key constraints in several areas. Our current measurement techniques are at their limits and can't take us to experiments with guaranteed discovery potential, but maybe CRES can. The QTNM collaboration is building on unique quantum techniques to demonstrate the viability of a CRES experiment, which provides the exciting possibility of having a large-scale particle physics experiment located somewhere in the UK, where we have this, where due to this kind of tritium infrastructure that exists. And I would just say thanks for listening. I'll leave it there.
Further questions?
How happy are your fancy amplifiers in big magnetic fields?
Not very, they have to be shielded. So you've got to either design the field so that you either design a field where they're far enough away that they're outside the stray field, or you put some kind of new metal shielding around them where you,
Without killing your trap.
yeah. Yeah, so it's an engineering, it's a design that, yeah, you have to overcome with these things, yeah.
For the atomic number densities you were able to produce with when you were testing the atomic source with hydrogen, do you expect similar results if you were using tritium, or how does that sort of scale?
I don't think the expected number densities are due to change too much. I think the mass is different, but the difference from hydrogen to tritium, I think the hyperfine structure is very similar. So I think that part doesn't change. Yeah, so I think we're working with tritium, and I think testing will move on to deuterium. Hopefully, tritium in the future will be able to answer that question. Yeah, but hopefully not too much, and hopefully this source is unoptimized, so it can go get to higher densities than what's currently been achieved.
I just had a quick question. For the atomic tritium beam that's in the CRES region, does the velocity of those atoms have to get folded into the tritium beta spectrum measurement?
Yeah, so you would have to do that, but the idea is that, okay, so at the moment the calculation is that for the hydrogen beam they're going 1,000 meters per second. It's less than that for the tritium just because of the higher mass. But because the beam is cold, you would hopefully be able just to subtract off that longitudinal velocity component because they're all going at roughly the same speed. And the spread in velocities is very small. So the forward and half maximum is like 20 meters per second
Okay.
at that beam.
So that's what helps you in that
Exactly.
spread.
Yeah.
Okay,
Yeah.
right, thank you.
This time I'll ask one more very naive question. So you talked about femtowatt powers, and then you said the HEMS have 7 Kelvin noise temperature, but I didn't get a sense of how much the quantum amplifiers value. I mean, what noise temperature do you need to see this power? Does it let you use fewer antennas, or what's the?
So, I mean, CRES has been observed with system noise temperatures of about I think the Jake 8 was order 100 Kelvin. It's about it's about that level, but it's more like, yeah, if you have a large volume system, you imagine a system of a lot of arrays, each antenna, for example, is going to be seeing a very small fraction of that power. So you potentially want to have as low noise temperature as possible. It also helps with, the lower you can get that noise temperature, hopefully the larger region of electron phase space you can access and measure. So it's all in the service of increasing those statistics. Really, yeah, so that's what it gets you.
All right, one more question. At one point you mentioned the down mixer.
Yeah.
What is that?
So your radiation, if you measure it at 1 Tesla, comes out and it's 27 gigahertz. But you can't digitize 27 gigahertz, so you have to mix it with like a local oscillator to mix it down to say, a few hundred megahertz to a region that you can actually sample with a conventional ADC or not incredibly expensive ADC. So that's what I mean by talking about down mixing.
That's what I thought, but I don't know how you do it.
Rita?
I'm just curious what you guys are working on in terms of the microwave detector right now.
As in
Yeah,
the antenna array or
Yeah.
yeah. So people at Swansea are fabricating arrays of patches, like small volume, but for the demonstrator at NPL there is circular cavity has been fabricated with a couple of probes in. So those are the two things that are currently in development, so they're both being explored, and I think hopefully we'll get the opportunity to test both of them in the demonstrator. Yeah, so those are the kind of two avenues that are being pursued. I don't think a firm decision has been made on the outlook for further ahead about which of those we want to pursue for a large volume. Yeah, but yeah, those are both being looked at the moment.
Thanks, Seb, again.